Hello everyone, I hope you are doing well. So in today's video, we are going to go through the 2023 VCE chemistry paper multiple choice section part 2. And so like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And here guys, let's mash through this video. Question 17. Lignite is a type of brown coal. When lignite is completely combusted in a power station, 19 megajoules per ton of energy is released. The efficiency of the power station is 39%. Wow, it is not very efficient. So basically, out of those 19 megajoules, only 39% is actually useful energy. The other one's actually wasted through basically the processes of getting that energy. What mass of lignite is required to produce 42 megajoules of usable energy in the power station? Beautiful. So, we know that basically we produce 19, so megajoules, it says megajoules per ton. So, mg over ton is going to be equal to 19. So, for example, if you have 1 ton, so you put 1 in this value here, so 1 times 19, you get basically 19 megajoules. Now, that's only if it's 100% efficient. Of course, it's not that because we know it's only 39% efficient. So what we're going to do is multiply this number by 0.39. And so what's that going to do? It's going to give us the actual real energy. So 0.39. So 7.41. So I think is 7.41. So for example, if you had 1 ton, you wanted to basically use 1 ton, it will basically produce 7.41 megajoules of energy. Not that 19 megajoules, because remember, most of it is wasted. All right. Now, we have this nice formula. Now, what mass of lignite is required to produce 42 megajoules? So basically just sub in 42 in here. So because in terms of megajoules, so just 42. And we can calculate T, which is your tons, so how much mass. Which is basically T is equal to 42 over 7.41. So 42 over 7.41, which is 5.68, like 5.66, somewhere around there. Yep. So D is your answer. Question 18. The graph below shows a HPLC calibration curve for folic acid. Beautiful. 1 milliliter sample containing unknown concentration of folic acid is diluted. Okay, guys, we have a dilution factor. Remember, we have a 1 milliliter sample and it was diluted to 1 liter. So I'm straight away gonna, from my memory, straight away find the dilution factor. So if we're going from 1 milliliter, which is basically 1.0 times 10 to the negative 3 liters, and we're gonna basically dilute it to 1 liter. So 1 liter. What's the dilution factor? To get the dilution factor, basically just divide this by this. Let's do that. So that's dilution. Why does it look like an O? Dilution. 1 divided by 1.0 times 10 to the negative 3. So our dilution factor is basically 1,000. This is going to be helpful if you're going to do calculations. So great, we have our dilution factor. Let's calculate it. The diluted sample is analyzed using the calibrated equipment at the same conditions. The folic acid peak area is found to be 0.35. What is the approximate folic acid concentration in the 1 milliliter sample? Yes, so 1 milliliter sample. So the original sample, not that, 1 liter diluted sample. So we're going to have to use our dilution factor, of course. So 0.35, where is that on the peak area? It's right over here. If we go down, what kind of folic acid concentration is that? It's, so halfway is 70, so it's around 18. So 18 nanograms per milliliter. Now be careful. This is not actually the 1 milliliter sample concentration. This is the diluted concentration. So to convert it, what we have to do is multiply it by our dilution factor. So this can be written nano. Nano is basically times 10 to the negative 9 grams per milliliter. And if you multiply by 1,000, which is basically 1.0 times 10 to the power 3, you basically get 18 times 10 to the power of negative 6 grams per milliliter. Which is basically 10 to the power of negative 6 is basically 18 micrograms per milliliter. From which one does that look like? Looks like C is your answer. Beautiful. Question 19. Compare omega-6 fatty acids with saturated fatty acids. Remember, omega-6 has on that, 6 carbon, it actually has a double bond. And that's what really defines what an omega-6 fatty acid is. With a saturated fatty acid, so a saturated has no double bonds, containing the same number of carbon atoms, alright, which of the following statements is correct? Omega-6 fatty acids have lower densities than saturated fatty acids. Let's think about it. Now, we know so the difference between basically omega-6 fatty acid is they have double bonds, whereas the saturated has just single bonds, overall. Now, what do we know? Remember, in those fatty acids, if you have double bonds, these create kinks. And kinks are basically, it doesn't allow the molecule to chain up or kind of to compress, meaning that its intermolecular forces are very weak. So remember, this is the kind of hint. The more kinks there are, so the more double bonds there are in a fatty acid, the lower their melting point is. All right. So because omega-6 fatty acid has kinks, because it is a double bond, it has a low melting point, compared to the saturated. So also density is basically, think of it as like a melting point, but of course density is how thickness it is, because it is, again, it has it has low density. So omega-6 fatty has low density than saturated fatty acids, and that is basically true. They do actually have lower density because of the weak intermolecular forces. Have a higher melting point than saturated fatty acids? Nope, they don't. Like we said, omega-6 has a very low compared to the saturated. Wrong. C. Have more hydrogen bonds than saturated fatty acids. Well, let's think about it. That's wrong, because if you think about it, if you have a double bond, look at the carbons. We can only have basically this is not in the case, but have a look at it. We can only fit 4 carbons because of the double bond. It actually takes some of those electrons. Whereas if we have, let's say no double bonds, we get 6 carbons. So because it's a saturated, we actually allow more carbons in it. So it would, what am I doing? More hydrogens. So have more hydrogen atoms than saturated fatty acids. Omega-6 does not have more. It has lower because of those double bonds, and hence, it doesn't actually fit a lot of those hydrogens. The saturated has more hydrogens, of course. D. Undergoes substitution reactions more readily than saturated fatty acid. No, that's the rubbish. It actually, because it has a double bond, it likely goes through an addition reaction. It has this more potential of going through an addition reaction. Because if you, let's say, for example, you have this, double bond here. When you react with, let's say, H2 gas through an addition reaction, basically that hydrogen goes from here and here, and it basically becomes, and that double bond breaks, of course, and then we got like a nice saturated molecule. So it readily goes through addition reaction, but no substitution. If you're doing substitution reaction, like subbing one of these to the other one, it doesn't go through that. That's really like a rare thing. It needs conditions for that, probably. So nope, absolutely wrong. Undergoes substitution more readily, not readily, probably hard. You need to give it energy, to be honest. That's, So A looks like the answer for that one. Beautiful. Question 20. Which of the following is always correct when performing an accurate acid-base titration? Water in the burette will dilute the alkyd. So let's think about it. If you have a burette here, and so if you have water in there, remember your burette has your standard solution, or what we call it, not a titrant. It has the titrant. It has that standardized solution. And if we have water in it, we decrease the concentration because we're actually diluting the standard solution or the titrant. So water in the burette will dilute the alkyd. Nope, not the alkyd, the titrant or the actual standard solution. So not that one. It's not basically like the most correct. Any acid-base indicator will give an accurate result. Not true. Acid-base indicators depends on the pH. Remember, if you look at your formula sheet or your data book, there's going to be like a list of different, of course, indicators where different pHs work. So not right. Water in the pipette causes an underestimate of the acid concentration. Okay, so let's say we had a pipette here. So we have a pipette here. And remember, your pipette has your alkyd in it. Alkyd. So if you have a pipette here, it has like that alkyd. So water in the pipette, if you have water, of course, if you have water molecules in it, in the pipette causes an underestimation of the acid concentration. Absolutely it does, because remember, your alkyd is the mix of the acid itself and the indicator. So if you're going to have water in it, it's going to basically decrease. It's going to dilute the concentration, and hence the concentration is going to decrease. So that looks correct. I've got to put a tick on that. The pipette is not tapped against the conical flux to ensure accurate volume delivery. Rubbish. I think it's better to tap it if you think about it. Because remember, if you want very accurate delivery, say, for example, if you have like a pipette and there's still water droplets still on the surface. And remember, if you want the most accurate, you want all the water to lose. So I think tapping it is the most best way, because if you tap it, all those water goes and you get an actual accurate volume. And so your calculations become more accurate. So the pipette is not tapped. Nope, it should be tapped actually. So I would say C looks like the best answer for that one. 21. Which of the following statements about denaturations is correct? Denaturation can only be caused by changes in temperature and the addition of acids. Now, we know denaturation is basically caused by temperature change or or pH change. Now, it says it can only be caused by changes in temperature, absolutely, or the addition of acids. So if you have an acid, it's going to decrease the pH. Now, be careful. They're just saying addition of acids. What about the addition of bases? Isn't that going to increase the pH? And hence, if you increase the pH, it doesn't also denaturate it. So this is actually a wrong statement because it doesn't really go. If it said it changes in temperature or changes in pH, that's your right answer. But it just says addition of acids, which is not kind of, it doesn't use that wide variety. It doesn't consider all the wide variety of answers. B, causes the reversible change of a protein shape. Rubbish. Denaturation causes the irreversible. You cannot bring it back to the original shape. C, hydrolysis is the primary structure of a protein. No, absolutely not. Remember, denaturation only affects the secondary, tertiary, and the quaternary structure of a protein, not the peptide linkages between them. Absolutely not. D, alters the secondary structure of a protein. Like we said, yes, it does. It actually alters the secondary, tertiary, and quaternary. 22. Methane, CH4, and methanol can be both used to power a fuel cell. Methane and methanol fuel cells produce the same amount of greenhouse gases and the same number of electrons per mole of fuel reacted. A different amount of... okay. So to do this, what I'm going to do is actually write the reactions. So let's have a look at methane. Now, we know methane, when it goes through combustion reaction, it goes through this. CO2, H2O. Where basically, of course, you want to get the moles, right? We have one carbon, so we get two of these, two, and two. Is that right? So 4, 2, 2. Yep, that looks good. So that is for this one. And what about methanol? So I know methanol has a 2 in front of it straight away. OH plus oxygen gas, because CO2 and H2O. All right, what do we see? So we have 2 carbons, so we're going to put 2 here. How many hydrogens? So we have 4, 8. We have 8 on the left, and we only have 2, so we have to put a 4 here. And oxygen, so we have 4 we have here, and we have here, so that's 4, 4, 8, that's 8. So if I put a 3 here, yep, so 6, yep, that works. Beautiful. That looks correct. And so be careful. Make sure they have the same. So we have 1 mole of methane. We also want to have, of course, 1 mole of methanol. We have here 2 moles. So basically just divide everything by 2. So if I divide this by 2, divide this by 2, what's 3 divided by 2? It's just 3 on 2. Divide this by 2, it gets rid of it. Divide this by 2, it becomes a 2 here. And so basically, yes, we have a nice reaction here. So methane, methanol fuels produce the same amount of greenhouse gases. Now remember, greenhouse gases are basically water and CO2. Let's look. You can see that we have 1 mole of this and we have 2 moles of H2O, which overall gives us a 3 mole of greenhouse gases. Whereas also this one too does the same. We got 1 mole and we have 2, so also this creates 3 moles of greenhouse gases, and hence yes, they do have the same amount. So C and D are wrong. And the same number of electrons per mole of fuel cell reacted or different? Wow, okay, that's a little bit more because now I have to rewrite them in terms of Harvey equations. All right, let's do that. So we have first CH4, and it basically gives, and it creates CO2, of course. All right, let's balance them out. We have 2 oxygens here, so we can actually add 2 H2Os here. Now we have how many? So we have 4, we have 8. We need to add 8 H pluses here, And so it gives us 8 electrons. Beautiful. What about the other one? So CH through OH goes to CO2. All right, what do we get? So we have 2 here, and we also have, okay, I'm just going to add a water because, so we have 2 oxygens here, 1 carbon, 1 carbon. And how many now hydrogens? We have, so 4, 5, 6. We have actually 6 H pluses. That gives us 6 electron minus. So absolutely wrong. They totally have different moles of electrons they produce. So different. Choose B. Which of the following is the semi-structural formula of 2-methyl pentane? Pentene, sorry. So pent, which is, so in the first one, so C, and has a double bond, and has 5 of them, so 1, 2, 3, 4, 5. And on the second, it has a methyl, so 1, 2. So here, it has a methyl. And basically that's it. So you basically just, so this is going to have hydrogen, 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 and we have hydrogens here. Beautiful. Now, to write the semi-structural formula, so we're going to start from this side. So we have CH2, all right, C, oops, CH2C, CH3, so we have that. Then we have CH2, CH2, and a CH3 at the end. So that looks like a semi-structural formula. Which one looks like that? Looks like C is our answer. Beautiful. Question 24. Which of the following statements about acidic propane 1-ol fuel cells is correct? Positive ions flow through the membrane to the cathode. So I'm just going to draw like a little sample thing, like a fuel cell here. Let's say this is your propane 1-ol fuel cell. So we have, of course, these 2 electrodes here. And we know, let's call this the cathode, which is basically the positive terminal. And we have the anode, which is our negative terminal. And normally in the cathode, in the anode is where the fuel is basically proposed. So your propane 1-ol. And in the cathode, it's basically where oxygen gas is basically pushed. And basically, of course, yeah. And because it's acidic, we're going to have H plus ions in the middle, which is your electrolyte. I mean, this is very basic, but let's see. So positive ions full, okay, before we know it's a galvanic cell, basically a fuel cell. So basically these positive go to the positive terminal. So yeah, actually these H pluses go to the cathode basically. Because remember, positive charges go to positive charges when it's a galvanic cell. So positive ions flow, let's see. So positive ions, which is H plus, flows through the membrane to the cathode. Yes, they do, from what we see here. The voltage decreases since the reactants are used up in half the reactions. Rubbish, because think about it. If it was a galvanic cells, yes, that is true. When you actually, when you lose reactants, your actual voltage decreases. That's why some batteries don't work, because the voltage is gone. There's no more reactant. But this is a fuel cell. And remember, a fuel cell has a continuous reactant supply. It's never going to basically, the voltage is going to be kept constant. It doesn't change and fluctuate. So rubbish. C. H2O is formed at the negative electrode and CO2 is formed at the positive electrode. Think about it. If our fuel is at the anode, we basically release some CO2 on the side of the anode normally. And on the cathode, we normally release H2O. That's what we basically release, because remember, if you have a carbon, fuel, basically some carbon, which is that C, comes out. So H2O is formed at the negative. Nope, it's formed at the positive cathode. So, right. Since it is a gas of O2, is the only reactant that must have a direct contact with the electrode. Nope, rubbish. Both reactants have a contact with the electrodes, not just one. I don't know what that means. That's just stupid. So choose A. Beautiful. Question 25. Below are the half equations for the lead acid accumulator cell. The lead accumulator cell can operate as an electrolytic cell. All right. So we have these 2. Which of the following correctly describes the lead acid accumulator cell when it's operating as a galvanic cell and when it's also operating as an electrolytic cell? So H plus ions react at the cathode, HSO ions react at both electrodes. All right. What I'm going to do is, okay, let's think of it in terms of galvanic cell. Now, how do I know straight away what would react? What would be like a reduction reaction or the oxidation reaction? Remember, they give us the voltages. The more positive and higher the voltage is, the more it goes through reduction, the more it's a stronger oxidizing agent. So this one here is more positive than this. So this one over here is going to be our reduction formula. This one. This is hence our oxidation. So reduction is going to go like this, which is, of course, your electrodes are going to be on the left. Whereas this one here, it's going to react like this to make sure electrodes on the right. So if I'm writing that, so if this is a galvanic cell, so GC, let's write those down. So reduction is basically PbO2 HSO4 minus plus 3H plus 2 electrons goes to PbSO4 plus 2 H2O. And so the other one's going to be Pb plus HSO4 gives us PbSO4 plus H plus 2 electrons. So that's what our galvanic cell reaction is going to go. And yeah, we can see that this here is your where the basically your cathode is. So cathode, this is where your anode is, and so basically this one's going for reduction, the other one's for oxidation. And so if this is like vice versa in basically in the electrolytic cell, you remember what happens? So electrolytic cell, they basically reverse. So this one, you reverse it, it's going to be it's going to react our anode, so it's going to go through basically oxidation, this one, and this one's going to go for reduction. So just flip them basically. So PbSO4 plus 2 H2O goes to PbO2 plus HSO4 3H plus 2 electrons. PbSO4 plus H plus 2 electrons goes to Pb plus HSO4. All right, so we've got those. Now, let's look at it. In a galvanic cell, H ions react at the cathode. Let's see. You can see that this one here is our H plus ions. And they are reacting at the cathode. Absolutely. Remember? So not these ones. This one is there's H ions being produced at the anode. But we're saying here, H plus ions react at the cathode. So yes. So it can only be basically not the anode one. So H ions react at, no, they don't. So you can see that they're not here. What about electrolytic cells? So let's look at the blue part here. HSO4 ions react at both electrodes. So let's see. Not true. You can see that they are basically being produced, not reacting at the electrodes. They are actually being produced. So H ions are being produced at both cathode electrodes. Yes, they are. This one's correct. Let's just see. Beautiful. All right. Let's do this question. A student investigated the viscosity of several biofuels. Remember, viscosity is the rate of flow. So the higher the viscosity, think of it as B. Like, what am I talking about? As honey. You know how it's very thick and it doesn't kind of, its rate of flow doesn't really, it has this resistance. It's like if you basically like throw it on someone, it's going to take time before it even leaves the vessel or, your cup. Whereas if you take water, it has a lower viscosity, so its rate of flow is higher, and you like throw on someone, it's going to really hit them quickly. So yeah, that's what viscosity is. The flow rate of each biofuel through a narrow glass tube was measured. The results are presented in the tables. Flow rate. So okay, flow rate of biodiesels produced using sodium hydroxide, and we got this. So we have alcohol used in biodiesel production with NaOH catalyst. Oil used in biodiesel, so sunflower oil, canola oil, methanol. There's so much happening here. Then flow rate of biodiesel produced using potassium hydroxide. Okay. So we have methanol, ethanol, sunflower, and canola oil. How many independent variables are there in this investigation? Of course, okay. Independent variables is the variable that you manipulate. It's the thing that you're changing. And so let's have a look. Now we have two of the catalysts. That's already first thing that came to my mind. I'm like, why we have so much, variables? Like we have NaOH and KOH. That is one independent variable because you can basically measure, like you're basically measuring between them. Manipulate them basically. That's one. Of course, we got also methanol, ethanol. comparing those two. So we can manipulate those. So that's also another one. And we also have sunflower and canola oil. That's also another one we're comparing. So 3 independent variables. That is what I'm looking at. And of course, your dependent variable is the rate of flow. Basically, it's 1 because everything's basically just measuring the rate of flow. 27. Select the most valid conclusion that can be drawn from the student's results presented in Table 1 and in Table 2. So, A. Biodiesels made from sunflower oil have a higher viscosity than biodiesels made from canola oil. So, okay, they have a higher viscosity. Remember, if you have a high viscosity, it means that you have a slow rate of flow because it's very slow. Whereas if you have low viscosity, you should have the high rate of flow. So what are we looking at? Biodiesels made from sunflower oil have a higher viscosity, meaning if it has a high viscosity, it has a rate, a very small number, basically. These numbers have to be small compared to canola oil, so sunflower oil. Okay, let's have a look at the sunflower oil in the first case. So we're looking at sunflower oil, and we want it, what was it? So we want it to basically be very low, because if we want high viscosity, it has to be very low rate. So I have a look at sunflower oil here, and between these two. So you can see that sunflower is lower than this. That's good. So it has basically a higher viscosity. Where about this one, these two? You can still see, yes, it actually works too, because sunflower is lower than canola oil. So this looks good. Let's look at another one. Sunflower oil, but oh no, it is bigger in this case than your canola oil. So that really ruins it. Whereas in this case, so the same. So sunflower oil and canola, we can see the sunflower oil does have a high viscosity. But there's a big problem this here. This kind of breaks the kind of pattern. So that's not the correct answer. B. Biodiesels are made from methanol, have a lower viscosity than biodiesels made from ethanol. So wait. Methanol has low viscosity. So low viscosity means the rate of flow is higher, and so it has to have a high number. So methanol compared to ethanol. High number. Okay, methanol. Let's have a look at methanol. We're looking at methanol here. So we want it to be higher. We can see, yeah, 4.8 is higher than 4.4. That's good. 5.1 is higher than 4.7. That's also good. 4.9 is higher than 4.4. And 4.8 is greater than 4. Beautiful. This fits all the conditions. So that is a nice conclusion. So B looks correct. Let's just rub these out. I don't want these to be here. Let's look at the next one. Biodiesels are unsuitable for the use in cold climates because they have a higher viscosity than petrodiesel. What the hell? This has nothing got to do with the question. It says select the most valid conclusion that can be drawn from these results. Nothing. We're not even comparing petrodiesel. There's no data that's comparing petrodiesel. So this is rubbish. Take that off. D. Biodiesels made using NaOH, so sodium hydroxide, catalysts have a lower viscosity than biodiesel made by potassium hydroxide. So wait. So using NaOH catalyst has a lower viscosity. Remember, lower viscosity means the rate of flow is high, so it has a higher number. So NaOH should have a high number. NaOH, so this one has a high number. Let's check. 4.8. No, it doesn't work. So this is supposed to have a high number then, but 4.9 is a bigger number when using KOH. So that's already breaking the rule. 4.4 and 4. These are the same, so there's actually nothing. 5.1 and 5. Yes, so this does meet the condition, whereas this one too, it also meets the condition. But remember, you already failed these two, so that's not a valid conclusion. So the only valid conclusion is B. Consider the fuel half cells equations and their half cell potentials in the table below. Alright, we have these. Okay, a galvanic cell contains this SO3 2- OH with a platinum electrode in the first half cell and M3 aqueous, M2 plus aqueous in the second half cell. All solutions are one more solutions than the cells is at SLC. The galvanic cells will deliver what? So 2.5 volts if the electrode in the second half cell is MNS. If 2.5 volts if the electrodes in the second is platinum. 1.57 volts if the electrodes in the second is Mn. Okay, so let's say we had the electrode as Mn solid, so Mn solid. Let's highlight what's basically going to react. Now, we know this is going to react, so S2O4, that's already O3, so where's that? This reaction, it's right over here. That could react. SO3 2-, which is this part here, and also that one here. OH, so OH are 2 here. Okay, nothing else. Mn3+, which is here. Mn2 plus, which is here, and Mn2 plus here. And because we have basically like the electrode as Mn, we also can, it's going to be here. That's another one. So remember, it's a galvanic cell. So to determine what's going to react at the reduction site or the oxidizing agent, it's going to be on the left, and it's going to be the highest one on the left, which is basically Mn3 plus. And so that's going to react and produce Mn2 plus. And remember, you do for the strongest oxidized one or the strongest reducing agent, it's going to be the down one on the right, which is Mn solid, which goes this way. So basically, what voltage should we produce? So it's this minus this. Let's do that. 6. That gives you 2.74, which is not even part of the answers here. Yeah, it's rubbish. So not that one. 2.5 volts we should be producing. That's rubbish. So Mn, and even this one, the same thing, Mn is, that's rubbish. So yeah. Okay, so let's say we did use a platinum. So if you use platinum, of course, you get rid of this. All right, let's have a try at platinum now. What happens if you use platinum? Platinum, okay, so same thing. So you look up, and it's the highest one on the left, which is the same reaction here. And you remember, you go down on the right side, and so it's this reaction here, which is basically this. So minus these two, what should we get? We get 2.5 volts. That's good. So using a platinum, it actually gives us 2.5 volts because platinum is basically an inert electrode. It doesn't even react, so that's why. Yeah, so B looks like our answer. We get 2.5 volts. Beautiful. Wow. All right. Question 29. Which of the following statements about mass spectrometry is always correct? The relative molecular mass of a molecule is determined from the base peak. Rubbish. Your base peak is the most abundant molecule or a fragment, basically. It doesn't actually tell you the molecular mass. The one that tells you the molecular mass is the molecular ion peak. Remember, so if you look at it like this, if you have like, I don't know, abundance here, you have the MZ ratio here. And so of course you're going to get this like high peak. That's where it's 100% abundance. That's your base peak, whereas you get some peaks here. But the one on the, like, basically on the right, the most highest MZ value basically normally tends to be the molecular ion peak, and that's the one that gives you the molecular mass of the molecule. So rubbish. B, the peaks in a mass spectrum are caused by presence of different isotopes. No, not isotopes, fragments. The molecule is breaking down because basically we shoot it with high energy electrons, and these electrons basically break down that molecule into positively charged fragments, and these are what is basically sent. So isotopes, when you're saying isotopes, it's like increasing the molecular mass. You're gonna, it doesn't make sense. So C, the base peak is formed when an uncharged species is removed from the molecule. No. Uncharged. Look at the word uncharged. Remember, they're fragments. They're always positively charged fragments. Now, yes, it is removed from a molecule. That's good, but it says uncharged. They are actually charged. They are positively charged. Wrong. D. The height of each peak is in the mass spectrum is measured relative to the height of the base peak. Yeah, could be, because if your base peak is 100, if you think about it, it's 100. This could be like, I don't know, let's say 20. Yeah, it's basically measured always relative to it, because this is what defines what it is. It's always the base peak because it's always 100 basically abundance, and so basically I think that's the last answer basically, because the other ones are all wrong, so it has to be D. Yeah, it can actually, the height of each peak in the mass spectrum is measured relative to the height of the base peak. Yeah, it can, because it's 100 abundance and basically everything's measured with it. Using it as a scale. Beautiful. 30. Last question. At standard conditions, a solution of hydrogen peroxide, iron nitrate, and this were added to a beaker. The initial concentration of H2O2, FeNO3, this in the beaker were all 1 mole. All right, so this is it. So they just added to a beaker. So it's not like, a circuit, so that's one thing. Just a beaker, and you're adding these things here. So if there is a spontaneous reaction, of course, you can actually just you can just produce chemical energy to thermal. I mean, that's the only possible solutions, chemical energy changes you can do. There's no electricity. There's not even electricity that will be produced here, because there's no wiring, in a way. And yeah, there's no path for electrons to flow. Let's look at which of the following statements is correct. Iron is deposited at the bottom of the beaker. Okay, before we even do this, let's just determine what's happening. We have all these stuff here, and they're in aqueous, so water is going to be basically also going to be reactive here. So water is going to basically be reactive, and these stuff. Let's have a look at our formula data book, and let's compare these. Let's look for these and highlight them. So, H2O2, which is where we got it, one here. We got, don't forget the waters. So let's just highlight those waters. Because it's H2O2. Also, we got H2O2 here. We get Fe3 plus, which is here. We also have Fe2 plus, which is here. And also, where was it? It was also another one, Fe2 plus here. And that is it from what I'm seeing here. Beautiful. So, okay, which one's the strongest reducing one? So if you go on the left and it's the highest one on the left, it's actually this one. So this one's going to be basically reduced, and hence it's going to be our strongest oxidizing agent. So basically this one, let me just highlight it here. This one here. Whereas the strongest oxidized one, or the reducing agent, is going to be the bottom one on the right, which is this one here. Goes like that. And so let's also highlight that. So no way, yeah, there's no Fe, there's no iron even produced here. It's just we're basically going to only produce, these are what we're going to produce. We're going to produce water, and we're also going to be producing oxygen gas. So there's not even iron even produced anywhere. So that's wrong. B, the two half reactions in the beaker immediately produce 1.09 volts. Rubbish, like we said before at the start. We're not even going to produce a voltage. There is no way, it's not even a circuit. We're just going to produce thermal energy. Just going to basically heat up it's just going to, be a spontaneous reaction between this and that here. So H2O2 and H2O2 again. So basically they're both reacting at the same time. And so yeah, they're going to react, and they're just going to produce thermal energy. You're not even going to produce any voltage. So absolutely wrong. Be careful with that. The concentration of H2O2 decreases immediately since it is the strongest reducing agent. So strongest reducing, it is the strongest reducing agent, but it's also the strongest oxidizing agent. Remember, it's acting as both. You can see here and here. Okay, so let's look at the other part here. The concentration of H2O2 decreases immediately. So wait, let's think about it. So we're saying it's a reducing agent which oxidizes. We can see that, yes, it is going to be decreasing, because, when you're forming oxygen gas, you're using H2O2. And when it's going through the opposite, when it's being also reduced in here, you can see that it's also being used. So it is going to basically decrease in concentration overall. But I think it's also, I'm going to put a question mark here, because it's also acting as an oxidizing agent. So it's, I think they should say not just reducing agent, but also oxidizing agent. So I'm going to put a question mark on that one, because it's merely correct, but just maybe missing a part. The temperature of the contents in the beaker decreases immediately when FeNO3 and react with H2O2. So wait, these two react. So let's think about it. Wait. Let's rub all these out. So H2O2 is still being basically, and all the water, and only Fe3 plus. So basically take these parts out. So what's our strongest reduced one? Still the same thing. And the strongest oxidized one? Still the same reaction. So there's nothing changed. So the temperature of the contents of the beaker decreases. Nope, they don't decrease. They increase. Remember, it's an exothermic reaction. It's going to be a spontaneous reaction between H2O2 and H2O2, so hydrogen peroxide. And so basically the temperature, the contents in those beakers are going to increase. The temperature is going to basically increase. Yeah, that's wrong. So it's only C. Yeah, I think, look, C is missing a part. I don't know if it's me. Could it? Because it should say also oxidizing agent, but yeah. I hope you guys enjoyed this video and learned something from it. Please make sure to like and subscribe and share this video with your friends. I hope you guys have a great day, and please take care of yourselves. Bye-bye.